Good morning, everyone. Welcome to our Future Science Missions and NASA Launches News Conference. Here to discuss some of our upcoming science missions is Waleed Abdalati, NASA's Chief Scientist. Amanda Mickiewicz, the NASA Launch Services Program Manager. Scott Bolton, the Juno Principal Investigator from the Southwest Research Institute in San Antonio. Maria Zuber, the Grail Principal Investigator from the Massachusetts Institute of Technology. John Grotzinger, the Mars Science Laboratory Project Scientist from the California Institute of Technology. And Daniel Stern, the NuSTAR Project Scientist from the Jet Propulsion Laboratory. And we'll begin first with Waleed Abdalati, NASA's Chief Scientist.
All right, thank you. Let me start by welcoming you here, and I just want to say very briefly, you're going to hear about some fascinating science missions today in a little more detail from my colleagues to my left. But what I really wanted to do is just take a second to remind you or state how science fits into the NASA portfolio. And really, NASA stands very strongly on three pillars. Human spaceflight, which is the most, I think, visible to many in the external community. Aeronautics, which some of you heard about in the previous hour. And science. And science, I'm the chief scientist at NASA, so science holds a special place for me. But it's really because of what we can do at NASA, what that science enables us to do. And if you think about it, I think there's a kid in all of us that's looking up at the heavens and wondering what's out there, what's it like? Is there life out there? Just full of questions. You were all on that camping trip or whatever when you were 5 or 6 years old and saw zillions of stars in the sky and just were filled with wonder. And I don't think that ever leaves us. And there's the adult in us that appreciates the beauty of the universe around us, that appreciates the beauty of the Earth from space, and that recognizes the need to understand our planet, how it functions, how it's changing, why it's changing, and looking more grandly, our place in the universe, how the universe works, how the solar system works, to answer really some fundamental questions that are at the very core of the human spirit, right? That drive us. It's in our DNA to explore, to understand, to learn, to try and survive in a changing world, to try and thrive in a changing world. And the perspective that we get from space, whether it's looking outward to the edges of the universe in the beginning of time, or inward, back at the planet on which we live, is unique, it's important, it fuels that hunger that's in us all. And you're going to hear today about a few missions. We have dozens and dozens, actually, but you can hear about a few that are up and coming and that are very exciting. So with that, I'll turn that over.
All right, thank you. Now we'll go to Amanda Mickiewicz. She is the NASA Launch Services Program Manager from the Kennedy Space Center. Amanda?
Thank you, George. Good morning. It's really my pleasure to be here today to be able to talk to you about the Launch Services Program and about some of the exciting missions that Waleed mentioned. First chart, please. We are Earth's bridge to space for all of NASA's robotic missions. So the missions that Waleed needs to have go to space to do all of the neat NASA science that we have in place and that we'll be doing in the future need a rocket to get there. And we provide that bridge to the rocket to get the missions there. Next chart, please. So what we do is we are really the broker between the spacecraft and between the launch vehicle. So if you see there on the chart in the upper left, those are the spacecraft customers that we work with. Several of them mentioned here today, Jet Propulsion Lab, Goddard Space Flight Center, Ames Research Center, Applied Physics Lab, many different places across the country, universities and NASA centers. We help them determine what the best rocket is that suits the requirements that they have to do their science missions. We also work with the telecommunication satellites, actually communication satellites like TDRS, in order to help them get to orbit as well. So we work with them very early on in the program, usually years and years in advance. As the principal investigators are developing the science and the spacecraft is coming together, we help them figure out which rocket will get them where they need to go. And then throughout the process, we work with them very closely in order to integrate all those requirements together to get to a successful launch. We provide the overall mission assurance for the integrated stack of the launch vehicle and the spacecraft. Next chart. We have been at the Kennedy Space Center since the late 90s. 1998, we were formed at Kennedy Space Center as the Launch Services Program. Since then, we've launched over 65 missions for NASA. They include many missions that you probably have heard of in the past. Spirit and Opportunity rovers, which have exciting science back from Mars. The Dawn mission, which you'll be hearing about more in the next couple of weeks. Be going to the asteroid Vesta. You've already seen some images from that. The Pluto New Horizons mission, we launched that back in 2006. That'll be arriving closest approach to Pluto in 2015, and then in the Kuiper Belt in 2016. And most recently, we launched the Aquarius mission from Vandenberg Air Force Base in California. That's an Earth observing mission that is studying the salt, basically in the surface of the sea, so that we can understand its effects better on the entire planet. Next chart. So we launch all these missions from a variety of launch sites across the country and really across the world. Our majority of our launches, over 50%, are from the Kennedy Space Center area at Cape Canaveral Air Force Station. We also launch about 40% of our missions out in California from the Vandenberg Air Force Base. We have launched a couple from Kwajalein and the New Star mission that you'll be hearing about later on. We'll be launching from Kwajalein Atoll. We've also had a launch out of Kodiak, Alaska. And finally, Wallops Flight Facility is also a site that we can use if mission requirements drive us there. So at all of these sites, we also provide payload processing facilities for the spacecraft to show up and do their final processing and preparations before launch. At any given time, we have about 35 missions in flow. While you'll see that we have 4 to 5 launches each year. Next chart, please. We typically work on 35 missions at any given time, and I know that's a little bit difficult to see, but this is to show you that NASA has a very healthy manifest of science missions and robotic missions coming up here in the next 5 years. The first mission there, 2012, the New Star mission, again, you'll hear more about that shortly. That'll be launching on a Pegasus launch vehicle. And then there is a good mix of Earth observing missions and also planetary missions and deep space missions that will be launching through 2016. Every couple years, there'll be a Mars mission that you can look forward to. Next chart, please. So more near term to us, actually in the next 4 months, and really completing in less than 4 months, are 4 big missions for NASA. The Juno mission, you can kind of see in that picture the huge solar array structure that it has. Those solar arrays will fold up within the Atlas V fairing for launch and then deploy. The Grail mission will be launching on a Delta II from Cape Canaveral. 2 spacecraft that will be joined together within the Delta II fairing. The NPP mission, that is an Earth observing mission that's multi-agency. Something interesting that we're doing with that mission, we've been putting a program together to launch very small CubeSat satellites for universities. There'll be several of those CubeSats on that mission. We're trying to provide capabilities on all of our launch vehicles to launch some educational satellites. And then finally, the Mars Science Laboratory, a giant rover that'll be going to Mars. And again, you'll hear more about that. That'll be on an Atlas V around Thanksgiving. So this is really unprecedented in terms of the tempo that NASA will be doing in the next few months. Some really exciting missions that have very precise timing for launch windows, and all the pieces come together in a really good fashion in order to make those launch dates. Next chart. And finally, I'll leave you with, we are on all of the media, Twitter, Facebook, the NASA app we're adding some information to, and also at the NASA website. Thank you.
Thank you, Amanda. And now to Scott Bolton. He is the Juno Principal Investigator from the Southwest Research Institute in San Antonio. Scott?
Hi, thank you for having me here. I'm here to talk about Juno, and after the completion of this next shuttle launch, Juno's the next one up. We leave August 5th, just a little less than a month from now, and we're going to Jupiter, and we're going on an Atlas V with the help of LSP that you just heard. Now, what Juno is really a voyage back in history. We're going back to Jupiter in order to really discover how the planets are made and what the early solar system was like. Can I get the first chart, please? So the reason we go back to Jupiter is it's the largest of all the planets. In fact, if you took everything in the solar system other than the sun itself, it would all fit inside of Jupiter. And so when you want to go back to the history and understand how planets were made and what was going on very early in the solar system, you really have to go back to Jupiter because it grew from the leftovers of the sun. So the sun formed whatever was left over, formed the planets and everything else in our solar system, and the majority of it went into Jupiter. And so we're very much about going back and almost figuring out the recipe for planets. And the way we're approaching that, the first step in understanding that recipe is we're back at the level of figuring out what's the ingredient list. And so we're going back to Jupiter in order to discover that ingredient list. We're looking for what's really inside Jupiter, how is it put together and built, and how does that represent how planets are made throughout the whole solar system and beyond, actually, in the extrasolar systems that we're seeing today with our telescopes. And so the next chart, please. And so here you see a picture of Jupiter, Jupiter with Juno, and you see these giant solar arrays that were already referred to. These things are massive. They're about 8.5 meters long a piece, so they're the size of a trailer for a big semi-truck. There's 3 of them, even with that, at the distance of Jupiter from the sun, which is 5 times the distance of that the Earth is from the sun. We're only getting enough power for a few light bulbs, but the spacecraft is very energy efficient, and these solar panels are pretty special. Solar cells are made to withstand that cold temperature and the low light conditions. And the whole spacecraft spins like a cartwheel through space and goes around Jupiter and goes into orbit around its poles. And you see the thing in the center there is the high gain antenna that transmits our data back. We launch on August 5th. That's when the window opens. It's about 3 weeks long. And we arrive in 2016. So it takes about 5 years to get out to Jupiter. And then we orbit for about a year. And we named the spacecraft Juno after the mythological goddess Juno, which was the sister and wife of Jupiter in Roman and Greek mythology. The Greeks did things a little funny there, so they were both the wife and the sister. But there was a story and a tale that went back in this mythology, in the ancient Greek mythology, and it was about the wife, Juno, was coming down and saw Jupiter. And Jupiter was being a little mischievous, as the king of gods sometimes was. And he saw Juno coming, and he didn't want her to see what he was up to. So he cast a veil of clouds around himself to cover what he was doing so she wouldn't be able to see. But she was already suspicious, and she was the queen of the gods and quite powerful herself. And so she used her powers to see right through the clouds and see the true nature of Jupiter. And that's exactly what our Juno, the spacecraft, does, is we use our special instruments when they get to Jupiter from a very special vantage point to actually pierce through the clouds and see inside and see the true nature of Jupiter. And we do that in a few different ways, and I'll explain those. So the science goals of Juno have to do with understanding the origin of Jupiter and how it was made and figuring out where we all came from and how the Earth was made and all the other planets. We do that by understanding this ingredient list that I mentioned earlier. So we pierce through the clouds with 3 different techniques. We use the gravity field, which goes right down to the center, and that'll tell us not only how Jupiter's structure and how it's spinning, but also whether there's a core of heavy elements maybe in the middle, or is it just gas all the way down? We don't really know that yet. The other thing that we do is we look at the magnetic field very precisely. And we do that because deep inside of Jupiter, the hydrogen becomes almost like a fluid and metallic, and it generates a magnetic field, like Earth has a magnetic field, but Jupiter's is much, much stronger. And in fact, it's the most powerful one in the solar system of all the planets. And so we'll see through to where that's getting created. We can't really do that at the Earth. We have a permanent magnetized crust on the Earth, so we can't see down to how our magnetic field is created. And so we'll see that for the first time at Jupiter. And we also have special microwave instruments that actually go in and listen and measure the temperature of Jupiter at various levels inside the clouds. So we'll see how deep those beautiful zones and belts go, but we'll also use that to measure how much water is in Jupiter. And that's a very important question to discriminate among theories of how Jupiter and the planets were made. And so those are our science goals are sort of divided into this thing that finally we do the polar magnetosphere. Because we go into polar orbit, we're perfectly suited to study Jupiter's aurora. And like Earth's, it's a really beautiful aurora, except it's much more powerful. And so we have a number of instruments that will go right over the aurora and measure how the particles are creating the aurora at Jupiter to teach us about that and allow us to compare it to Earth. Okay, so can I get the next chart, please? So of course, the mission Juno couldn't happen without a great team, and we have one of the best. And here you see Juno in its final stages of preparation. It's a Lockheed Martin spacecraft, and you see the solar panels folded up against its side. They get tucked into the payload fairing, and then they open up about an hour or so after the launch. And they unveil it, and then the power starts surging through the blood in the veins of Juno, and then it's on its own. It's spinning, and it sends its way to, they send it to Jupiter. So you see a couple of guys in the clean room there working on it. Okay, the next slide, please. And so there I'll leave you with our graphic design for Juno, and the website is listed on the bottom. You can learn a lot about Juno from looking at that website. There's also a website at NASA as well, nasa.gov/Juno. And I thank you. I look forward to seeing you all at our launch next month.
Thank you, Scott. And now we'll hear from Maria Zuber. She is the Grail Principal Investigator from the Massachusetts Institute of Technology. Maria?
Okay, thank you very much. I'm really thrilled and excited to be here and talk to you today about the Gravity Recovery and Interior Laboratory mission, which is going to use radio signals to reveal the mysteries of the moon. If I could have the first chart here. Okay, so that shows you the different radio signals that go between the two spacecraft. GRAIL is the first formation flying mission to another planet. So technologically, it's blazing the trail for other missions that will want to go to different planets and use coordinated observations to make measurements. And a very important thing is timing. So here are some schematic of the two spacecraft. So here I'm the sun, and the solar panels are pointing at the sun to power it. And all of you people in the audience there are in the direction of the moon. And these two spacecraft will fly in tandem in a polar orbit around the moon, about 55 kilometers above the surface, and about 200 kilometers apart. And as the first spacecraft passes over a mass anomaly beneath the surface of the moon, it will accelerate or slow down, and its distance will change with respect to the second spacecraft. And by measuring tiny distance changes, we will be able to recover what the interior structure of the moon looks like. Now, measuring the distance between 2 points, I tell people, is not very hard. It's something we fundamentally learn very early on in school. But we can measure the distance between these two spacecraft to less than the size of a red blood cell in humans. So a few tenths of a micron per second in the velocity of these two spacecraft. So it pays to learn how to measure the distance between 2 points and to learn it well. So if there are any kids out there watching, study your math. If we could have the next graphic here. All of you probably remember how it used to take 3 days to go to the moon, and the Apollo Saturn V went to the moon. Well, we wanted to take longer to go to the moon, because if you leave Earth and you go barreling to the moon, you need a lot of fuel to slow down, and we wanted to use small spacecraft and small fuel tanks. And so as a consequence of that, we use something called a low energy trajectory, where we go out to a point called the Earth-Sun Lagrange point, which is essentially like a buoy in the ocean, if you have a boat that comes around and comes to the buoy. So we take 3.5 to 4 months to get to the moon. Now, in addition to saving fuel, what this allows to happen is that these two spacecraft will arrive at the moon on the same days, no matter what day in the launch window we launch. So we can completely decouple the operations in cruise to the operations around, and it adds simplicity and reduces our risk. And it also allows us to do two critical maneuvers. Each of these spacecraft are going to insert into orbit around the moon separately, and it allows us to space these maneuvers out by a day, so we're not doing two critical maneuvers on the same day. Okay, if I can have the next slide, please. Here are the two spacecraft in testing. The spacecraft are designed, not exact copies, but after the XSS-11 spacecraft, which was a military spacecraft built by Lockheed Martin in Denver. So we used essentially declassified military technology and took advantage of that. These two spacecraft, they're about the size of a washer and dryer in your house, so they're very compact, but they're as big as they need to get the job done. The spacecraft also uses instrumentation that was built from the Jet Propulsion Lab, which is essentially a simplification of the instrument that was flown on the GRACE mission, the Gravity Recovery and Climate Explorer, that is still operating around Earth. We took that technology and made use of that. What we had to figure out to do at the moon, GRACE uses GPS to coordinate the timing between the two spacecraft. There's no GPS at the moon. That's what we had to figure out to do at the moon. And now that we figured that out, we have the ability to time correlate spacecraft around other planets. I will also say that these two spacecraft arrived down here at Cape Canaveral a week earlier than we proposed in our original proposal, and the spacecraft the mission is on budget, on schedule, and ready for a September 8th launch. Now the final chart here. Let me tell you about what we hope to learn about this. So there have been many missions that have gone to the moon, orbited the moon, landed on the moon, brought back samples of the moon. Those samples are still a treasure that we continue to study today. But the missing piece of the puzzle in trying to understand the moon was what the deep interior was like. And so if you look at the surface of the moon or the other planets, the moon is really the most accessible example of an old surface of a terrestrial planet, okay? All the terrestrial planets, including the Earth, looked like that, and what you see on the surface of a planet really records the entire history of the planet over 4 billion years. So the surface of the moon there is 4 billion years. Earth used to look like that 4 billion years ago. What the surface of the time of the age of the surface of the moon is actually about the age of the Earth at the time that the first cells were developing on Earth. And that record of time in terms of what was preserved on Earth is not preserved well at all. It's a few grains, it's not surfaces. But here we have a planet that has evolved. So what we can look at is the external influences, such as impacts that have shaped the surface. What was going on in the interior? How did it melt? Is there a core? How did the core form? How did the interior convect? Why is the near side flooded? Why are the impact basins on the near side flooded with magma and give us this man in the moon shape that we look at, whereas the backside of the moon doesn't have any of this? So those are all mysteries that, despite the fact that we have studied the moon before, we don't understand how that has happened. And GRAIL is a mission that's going to tell us that. So we are extremely excited about that, and if you come back on September 8th, we are going to get to the launch pad on time. So,
thank you, Maria. And to discuss our next mission after GRAIL is John Grossinger, the Mars Science Laboratory project scientist from the California Institute of Technology. John?
Thanks. It's a pleasure to talk to you about Mars Science Laboratory today. In a little while, I'll walk you through our rover here called Curiosity, named for the great property of all scientists, which is to want to explore things that you've never understood or been able to see before. I'll come back to that in a minute. Curiosity is really the latest installment in the Mars exploration program. And I think many of us would not have imagined, having started on Mars exploration rovers, one of which is still moving around today, that we would ever really get on to this next step. Curiosity is as big as a car. It literally weighs a ton. It requires a whole new entry, descent, and landing system in order to get it safely to the surface called Sky Crane, which hovers and drops the rover down on a set of bridles. And then when it feels it's touched the bottom, Sky Crane flies off, and the rover is pretty much born ready to start driving. It's designed to drive 20 kilometers, and it has a nominal lifetime of 2 Earth years. So if you scale that to say Opportunity, which was built to go 300 meters and has now gone 30 kilometers, and was supposed to last 9 months and is now working on 7.5 years, we've probably got a pretty good mission ahead of us here. So if I go to the first slide up there, here you see sort of the history of rovers and the development of the Mars program. There in the center is Sojourner rover, part of the Pathfinder mission. That's about as big as a small microwave oven. And then on the left side, you've got the model for Spirit and Opportunity. Opportunity, of course, still rolling today. It just passed, I believe over the weekend, it drove 31 kilometers across that barrier. It's about as big as a golf cart. And then on the right in the back, then you've got Mars Science Laboratory, which is about as big as a Mini Cooper. It has the wheelbase of a Humvee, and the arm out in front of it weighs about 85 kilograms. That would be like trying to pick your lawnmower up in front of you and hold it up. And that's where all our instruments are that touch the surface of Mars there. It's got the same rocker bogie suspension that was originally implemented on Sojourner as part of the Pathfinder experiment. It's been so successful, we've continued to work with that. Okay, so in the next one, what you can see here is a view from ATLO and JPL. The rover just shipped here to the Cape just a few weeks ago, and you get a side view with some of the engineers in the background there. The arm is partially deployed out in front. If you were to extend that all the way vertically, it could dunk a basketball. So it's tall. And if we get up to interesting rocks, we'll be able to reach up quite high to study them there. Okay, then in the next one, we have 2 landing sites. This has been an amazing process, and I think besides the development of the rover itself, this entry, descent, and landing system that JPL designed is so robust that for the first time in the history of Mars exploration surface missions, the scientists are able to choose the landing site where they want to go to. So we don't just hope that we land in a place that looks like something attractive might happen. We've actually been able to have a process where all the best sites rise to the top, and all of those are available for discussion. And what came out of that is a final 4 that we then went forward to with headquarters, and we're engaged in a set of iterative discussions there. We're down to the final 2, and this is one of them. And what you can see there in the black circle is our landing ellipse, which is 20 by 22 kilometers, rather than MER, which had a landing ellipse of about 150 kilometers in diameter by 80. So we can land in the flat spot of this location called Gale Crater. That crater is about just over 100 kilometers in diameter. And then to the left of the landing ellipse, towards the top of the image, you see a mountain which is about 4 kilometers high, almost 5 kilometers high. So that's higher than Mount Whitney. It's higher than the highest mountain in the lower 48 in the US. And our goal is to climb the base of that mountain initially. And there's a stack of layers there that looks like if you gaze into the Grand Canyon and wonder what all those layers are. Those are chapters in the history of the environmental evolution of Mars, and what MSL is going to do is explore the early environmental history of Mars with an emphasis towards habitable environments. And habitable environments are those environments where you have a source of water, a source of energy for microorganisms to be able to metabolize, and then a source of carbon for them to be able to build structures as we know life is based on here on Earth. Okay, so the next one then shows the other competing landing site, which you look at straight down on this image from Mars. It's a delta. It's an old dried out delta. This is probably the best place on Mars where you can look down, and if you ever wanted to know if there was a standing body of water where microorganisms could possibly live, this is the place. And so here you don't have the great thick succession that you have in Gale Crater, but you've got something which is a really bright target potentially for a type of environment that might preserve organic carbon, and MSL comes equipped with an instrument to be able to detect organic carbon if it's there. So we go back and forth between these. We love both of these as the finalists. We don't know yet where we're going, but it'll be one of them. And when we get there, then one of the main operations that we're going to do, which has been different from the previous rover missions, is we've got this heavy arm that sticks out in front, and in the front of this arm, we've got a drill. It's like the kind of drill you'd go to buy at Home Depot if you had to drill a hole in concrete. So we drill the hole in the rock down to 5 centimeters, collect the powder, then pass the powder back up into the top of the arm, sort of shake it back and forth slowly, and it sieves through until we get the really, really fine-grained stuff. And then we dump it into the top of the rover. So these are ports that allow us then to get access to one instrument that does X-ray diffraction. That'll give us the definitive mineralogy that we wonder about from orbit. But these other 2 ports that you see are here goes down into an instrument called SAM. And in that instrument then we're able to heat up the rock and turn it into gases and study those gases, including look for the presence of organic carbon. So this rover is really a mobile chemical laboratory that we take to the surface of Mars. So our launch date is on Thanksgiving Day, and we hope to see you all there. Thanks very much.
Thank you, John. Our first mission of 2012 is NuSTAR. And here to talk about that mission is Daniel Stern, the project scientist from the Jet Propulsion Laboratory, JPL. Dan?
Thank you for this opportunity to talk about NuSTAR a little bit. NuSTAR is a nuclear spectroscopic telescope array. It is a high-energy or hard X-ray astrophysics mission. Unlike the other missions we heard about today, which will study objects in our solar system like the Moon, Jupiter, Mars, NuSTAR will spend most of its lifetime looking at objects far beyond the solar system, including distant galaxies and black holes in distant galaxies. NuSTAR works in the high-energy X-rays, slightly higher energy X-rays than the Chandra X-ray Observatory, which you might have heard of. Chandra launched on the Space Shuttle Columbia back in 1999 and is continuing to do fantastic science. Can I get the first slide? So the bottom left shows a picture of NuSTAR taken last week at Orbital Sciences Corporation in Dulles, Virginia. The observatory is almost fully integrated at this point. In about a week, it will enter into the thermal vacuum chamber for a series of tests in flight-like conditions. And everything's on schedule for a launch in early February on a Pegasus rocket. The larger image is an artist's conception of what NuSTAR will look like on orbit. And it has a slightly unusual design because the high energy or hard X-ray optics require a very long focal length or very large separation between the lens or the optics and the detectors on the other end. And we achieve that with a 10-meter or 30-foot mast, which extends about a week after we launch. NuSTAR will be the first focusing mission at working at these high-energy X-rays, which gives us a factor of more than 100 gain in sensitivity compared to previous missions. Working at these energies, can I get the next slide? And so this shows you what you gain with that focusing optics. You get a much crisper image. The top picture shows you our view with current technology of the center of our own Milky Way galaxy, obtained with the Integral satellite a couple of years ago. The bottom image shows a simulation of what we expect to achieve with the NuSTAR. And we resolve with the sharper images achieved with the focusing optics of NuSTAR, we resolve those half dozen sources that you see with Integral into several hundred sources, which in the galactic center are mainly black holes and neutron stars, as well as the 4 million solar mass black hole in the center of our galaxy. NuSTAR has a range of science objectives. We will spend 2 weeks studying the sun. We'll look at microflares and nanoflares on the surface of the sun, which are thought responsible for heating the solar corona. We'll look for possible signatures of dark matter decay coming from the center of the sun. And then we'll spend a lot of the mission looking at both objects in the Milky Way galaxy, black hole, binaries, neutron stars. And then one of the main objectives of NuSTAR is to study black holes in the centers of other galaxies. We work at similar energies that doctors and dentists use to probe inside your body. NuSTAR will use these high energy photons to study what's going on near black holes in the centers of galaxies. We think that supermassive black holes are a universal property of large galaxies, but many of them are heavily obscured and shrouded in gas and dust. And NuSTAR will use these high energy photons to study what's going on underneath that enshrouding material. We're on schedule for launching in February, and Thank you for having me here.
Thank you, Daniel. We're ready now for questions. Please give your name and affiliation when the microphone comes to you, and we'll start right here on the front. Right here.
It's Leo Enright with Irish Television for John Grotzinger. I'm sorry, I didn't realize you were down to 2 landing sites. I think I was traveling and I must have missed the announcement. But could you clarify again what the second site is? It wasn't absolutely clear from your presentation. Could you talk a little bit about why these were picked over the other 2? And could you talk about where phyllosilicates specifically come into this and where was that still a critical part of your decision-making process?
Yeah, I'll work backwards there a little bit. All the landing sites have phyllosilicates, and the 2 finalists, Gale and Eberswald, Gale, in addition to phyllosilicates, has a very thick sequence of sulfates. And so Gale is the site where you get to traverse through, initially in the nominal mission, it would be hundreds of meters, first of phyllosilicates, clay minerals, and then over that into sulfates, and deposit an environment that geomorphically looks like it could have been a ponded, pooled, possibly lacustrine-type setting. In contrast to that, you have Eberswald, which shows only phyllosilicates, in which you see you're at the tip of a delta, so the rover would drive up to the toe of the delta and sample the layers that are at the base of the delta, where from orbit we see the phyllosilicates concentrated there.
Additional questions? Right here.
Jim Siegel, Celebration Independent newspaper. Perhaps a question for Waleed. We've seen here a number of projects that are going on in 2011 into 2012, and I think it was Amanda who showed us the other things happening in the next few years. How do all these missions fit together? They each one have a specific purpose, but I'm wondering if there's kind of an overall coordination of all of this. What does it all mean, in other words, rather than just what does each individual mission mean by itself?
Well, certainly each individual mission is targeted at a specific science objective. It would not have been selected for development were it not to deliver some valuable science in and of itself. In terms of the big picture, what it all means, it comes back to what I said in the beginning about the kinds of questions that the child in us likes to ask, but the adult often suppresses, which is, what's our universe like? How did our solar system form? How did our Earth form? Where are we headed? How do galaxies form? You know, what is our place in the universe? Are we alone? There is a collection of, I think, fundamental questions that it's really in our nature to just try and understand the world around us, the universe around us, the sun that fuels life on Earth. All of these work together to really help us, I guess in the simplest sense, understand the universe that surrounds us and our place in it.
Ken?
Ken Kramer for Spaceflight Magazine for John Grotzinger, please. Can you tell us when you will make this final selection? Will this be after the launch? And your landing ellipse in Golly Crater is very narrow. I mean, how confident are you can not land on top of the mountain instead of on near the edge there?
The decision will be made in the next couple of weeks, I'm told, by headquarters. So I think by the end of July that will be public. As far as the landing ellipse goes, that's a 3 sigma error landing ellipse, and so the probability of landing outside of it is really, really small. So we have a lot of confidence that the smaller landing ellipse, there's even as we get closer to launch, I think you can expect us to shrink it down even further as the calculations run out a little bit further. But it looks very safe to land in. We have no concerns about that at all, which is what enabled the sites finally in the last instance to be considered on the basis of science, pretty much only on that reason.
Any additional questions? Yes, right here.
Sawyer Rosenstein for Talking Space. The question is for Amanda. I was wondering what process you used to decide the launch vehicle for each mission, if you could explain that, please.
Sure. Typically what we do, or I guess always what we do, is we work with the mission very early on to let them understand what the capabilities are of the launch vehicles that we currently have on the market or on contract. It's based specifically on what the orbit requirements are of the satellite, what the mass of the satellite is, what it needs to do from a science perspective. And we put all that together and decide which rocket it'll fit on top of physically, dimensionally, and also analytically. And then as we go forward through the process, we provide those requirements out to the launch service providers that we have available to us, and we compete that amongst those providers. And the one that can meet those requirements the best will be selected. Okay.
Further questions? Yes, right here. Yellow shirt back here.
Yeah, Randy Atwood, Spacecraft Interactive. Question about the Grail mission. Could you talk a little bit about the imager that's flying on the mission that's there specifically for education and public outreach?
Certainly. Certainly. So Grail is the first mission to fly an imaging system that does not have a scientific objective. Okay, this imaging system, which is called the MoonCam, is devoted entirely to education and outreach. The investigation is led by Sally Ride, who now dedicates her life to working with middle school students, particularly young women, but all students, to raise their awareness and understanding of science, math, and technology. And these cameras, they're essentially rocket cams, the kind of cameras that we put on the rockets to see the stages separate. So they're not very expensive, and this investigation, it's totally best efforts. Okay, there are no requirements for number of images that we have to get. Each spacecraft will have camera electronics and 4 camera heads, so that we don't have moving parts, and middle school students will be able to log on, and if their school is registered in the program, the software is available to see where the Grail ground tracks will be passing over, and then students can target images of something they'd like to take a picture of and input that to the system. And then there is a mission operations center that Sally runs out at the University of California at San Diego, where college students run this and get the software input. And then we take as many of these images as our operations allow. But this is done in a completely non-interference basis with the gravity mission. So in the gravity mission, the spacecraft are just ranging to each other constantly. We don't move the spacecraft around. That actually interferes with gravity. We just want to put them in orbit and let them fly and watch how they get perturbed by the moon. So the way that we were able to do this, make it cost-effective, not introduce risk in the mission, was to make it entirely best efforts.
Question here in the front.
Jonathan Amos from BBC News. Question for Scott about Juno. What was the thinking behind going with solar panels? Rosetta is, I think, the most distant spacecraft currently with solar panels. You'll break that record. Why not go with an RTG? Is it a cost issue, a practicality issue? What is it?
It was primarily a practicality and risk issue. Back when we were formulating Juno as a principal investigator mission, the way it works is NASA puts out an announcement of opportunity, and different teams come together and compete. And when we were putting that together, there wasn't really an RTG available anymore. There was a plan to develop new ones, a new kind that we would be able to use, and they advertised that as a possibility. But when we looked at it, I thought, the team kind of thought, well, there's some risk that development won't happen on time, and or the cost will go up higher than we predicted. And so we looked at whether there was an alternative of existing technology, or with a small leap, which was what the solar cells represented, we needed to. And so we judged it as a smaller risk to actually go with the solar power, and that was primarily what if there had been RTGs available, we may have gone that way, because it would simplify operations. I mean, as a solar paneled mission, we have to keep those solar panels facing the sun. We never go into Jupiter's shadow. Those are things that we can do and still accomplish all our science. It doesn't hurt us at all, but it would have been easier if we just could have pointed any way we wanted. And so we've been able to develop that, and in fact we've advanced solar cell technology, so that's also good. I like to say that we're green, and we were green before it was in to be green. But I also wanted to let you know, I'll take this opportunity to, that we also have a camera on board that's strictly for outreach. There's no science requirements, very similar. And not that I want to battle Maria, she's a good friend, but we're launching first.
We're getting there first.
Yeah, but I'm going to turn on that camera before you get there. Now I know I have to.
Have we any additional questions? More here in the front. Here.
Jim Siegel, Celebration Independent News. I have a question for Amanda regarding the launch capacity of KSC. With all of the news now about the shuttle going, concluding, and potential layoffs here in Central Florida, I'm interested in whether your organization also coordinates launches for the commercial side of the business, and what is the capacity of Kennedy Space Center or the adjoining Air Force Base to launch vehicles? Are you going to use many different pads, just one or two pads? How is that going to work?
Sure. So we don't coordinate missions for commercial. They do that themselves now. DoD coordinates their own missions as well. All of our launches are from that are in Florida are from Cape Canaveral Air Force Station, and it's really depends on which launch service provider that you're using. So, for instance, United Launch Alliance has the Atlas V that we have 2 of our missions launching on this fall. Typically, the launch flow runs between 60 and 90 days, depending on the complexity of the mission. So, so the timing between Juno and MSL is larger because both missions are very complex. For the New Star mission, which will be launching out of Kwajalein, we like to have a larger separation there because the travel time is a good bit. You have to integrate the spacecraft at Vandenberg Air Force Base first before you actually ferry it under an L-1011 on a Pegasus rocket to its launch site in Kwajalein. So typically we like about 30 to 60 days between missions if we have one out of Kwajalein, just to make sure that we can get everything. Once you get there, logistics are a little bit more difficult to handle. So you like to have a little bit more separation time between that mission. So it's really very highly dependent upon which rocket you're using and which provider you're using. And then the science requirements as well of the spacecraft that drive the actual window that they need to launch within.
Ken, you had a follow-up?
Yes, Ken Kramer for Spaceflight Magazine. A quick one for John and Scott. For Scott, quickly about the EPO camera. Will you take any approach images of Jupiter? I understand you're deciding whether to do this or not. And for John, can you talk a little bit about the sampling, how many samples you can take? Will you use them up on the primary mission all, or will you save some of that sampling possibility for the extended mission? Thank you.
So you want me to go first? We will take some not real distant approach shots. Our camera's, it's a outreach camera, so it was very much a best efforts basis, the same way Maria described it. And it's designed in order to capture the first images of the pole when we go over the poles. And also, we go very close to Jupiter. At closest approach, we're only 5,000 kilometers above the cloud top, so we're really right on top of that baby. And so you'll see images that are really, for the first time, giving you details of these beautiful clouds and zones and belts and swirls. And so that's really what the camera is designed to do. It's a color camera. And so far away, we won't be able to get very good images. It's not one of these, narrow and wide-angle cameras that you have on some flagship missions. And so we'll get a couple of shots, but they probably won't be great outreach shots. It's mostly the closer-in stuff that we'll get.
As far as MSL goes, there's a couple of different ways that we'll do sampling. The most involved sampling is when we actually drill and then pass a powder into the rover. We have no mission requirements about when we must collect samples. And I think what we learned with MER is that studying rocks on Mars is much like that on Earth. You don't want to sample everything that you come across because not everything that you come across is interesting. So we'll high grade it if it turns out that there's really exciting stuff halfway through the nominal mission. Then we might collect a lot of samples, or we might choose to defer till later on. So we have that flexibility. Now, we do have remote sensing as well that features a lot of excellent cameras, plus a laser that creates a plasma up to 7 meters away. So as we're driving along, we will be zapping this laser all over the place, getting elemental chemistry. So we'll have some record of what we drive by that we don't do more involved sampling with.
Thank you, John. And that means our next launch after STS-135 is almost right away. It's Juno on August the 5th on an Atlas V. So stay tuned. Thank you.